You can turn off the lights. I like it dark.
It's okay, I'm recording.
It's better to see the power. Oh, no,
He's got his own.
I got it.
Oh, whoa, look at you.
Also,
should.
good.
Alright, whatever. We're going. Okay, so. Dude. What is this?
Dude, that's a.
Dude, Anthony, what you do?
I got you,
That's
dude.
the end of
You
the
ready
series.
for this?
He's gonna.
Come on, baby.
Oh.
I need a damn, dude.
Alright, that works. Thank you. Okay, so my project is I made a cruise control circuit, and I was going to demonstrate it, but I mean we already put the ramp down. I don't want to put it back up again. I'll demonstrate it after the PowerPoint. Okay, so first things first. What I was going to demonstrate, I was just going to connect two batteries like directly to the motor and just turn it on and let it go. So what it does is during like when it's flat right here. You know, the voltage is going to stay 3.2 because that's, you know, the battery voltage. And it draws 0.4 amps of current just by itself because it has to react to the load, like forces of friction, rotational energy, everything it has to account for to move the car. Once it hits the ramp, it starts decelerating because now it has to counteract the potential energy that it's going through. And also, for some reason, it starts pulling 1.1 amps of current. It just kind of takes care of itself. At the top, same result, 0.4 amps. And once it goes down, it starts drawing 0.2 amps just by itself using just AA batteries. And it starts accelerating because of the force of gravity. So, I found that a little weird, and I put up how much power, you know, P equals IV. So the power does fluctuate across the motor, and the problem with that was, I thought, at first, if I just put it, like, I thought a motor was just controlled by its current. So I thought, hey, if I get 1.1 amps of current going through it, when it hits this, then, you know, it's going to go up. So, I didn't put this slide in, because I just realized I forgot. But I tried it with just one delay. I was like, you know what, if I change half the voltage, it'll go half as fast. But I mean, here at one battery, it stayed the same. It pulled the same amount of current. Right here, it still pulled 1.1 amp, but it just stopped and it didn't even go up the ramp. So I was like, okay, so now I guess from that, motors are more like power controlled, not necessarily just current, because same current but without the same voltage didn't give me the same results. Okay, so this is basically my cruise control circuit. I have my accelerometer, which will measure the tilt of what the car's on. That will get sent to an op amp. Damn it, Java.
Java update.
Yeah, I say yes like every other day, but it still comes up. Who knows how many updates there are? Okay, so anyway, the accelerometer goes to the op amp, which amplifies the voltage, and then that gets sent to the voltage regulator, which kind of amplifies the current going. And then that just gets sent to the motor and the gear train. So first things first, the accelerometer. I'm using an ADXL327, which is a 3-axis sensing accelerometer. Here's just, you know, a diagram of the thing. And by 3-axis sensing, I mean it has, like you can see right here, it says X, here's Y, and then out would be Z. So depending on how you orient it, it'll give you, you know, an output response. So it's kind of low drain because it only takes 3 volts of power, roughly 375 microamps that it puts into it. But the 0G bias level, that means if it's flat completely and it's feeling no forces of gravity, it's going to output 1.5 volts. And for every increase or decrease in like for every increase in G it feels, it will put out 420 millivolts more. So how does that work? So for this, I'm only using 1 axis because really you don't need 3 axes for this. But I'm using the x-axis, and basically this black box is just the accelerometer. So when it's perfectly flat, it's feeling 0 G's of force because like as it's rotated, like the force it feels is dictated by this equation, just G times sine theta. So when theta is 0, sine is 0, you're feeling no forces of gravity. When it's tilted up, you'll feel, you know, the sinusoidal factor of G. So on the ramp, basically just exactly what I said. Now here theta is 28 degrees, here it's 0, here it's negative 28 degrees. You know, just running the math, you would feel an increase of almost half a G, you feel 0 G's in the middle, and negative half a G when you're descending. And just measuring that, just putting the accelerometer on that, it's giving me those volts. That's what it's basically outputting, like when it's on each ramp, right? 1.47 on the incline, 1.30 when it's flat, and 1.13 when it's descending. So, that was the accelerator circuit. I'm just showing you piece by piece, and I'll tie it all in together. Hopefully, it'll make sense. Okay, so this is my op-amp. I'm using the MCP6231. And basically what I'm doing here is, let's go back to the last slide. Previous. Okay, so right here, the minimum voltage I'm ever going to see from my accelerometer is 1.13 volts. So what I'm doing, it sounds a little complicated, but just trust me, it works. So my accelerometer is 1.13 volts at its minimum, and I'm just using a summing amplifier. So I put this potentiometer, so it'll also have negative 1.13 volts. So when you add this plus that, the op-amp sees 0 volts when it's descending. Okay, and then my gain is 1 plus R4 over R3, which is 11. So this is basically what I was talking about with the whole the op-amp. I'm going to call it the sum, which is the sum of the potential and the accelerometer. So at 0, the op-amp will be outputting 0 volts, because 0 times 11 is 0. Then when it's on the flat, right here, that's this 1.3 volts, which is what the accelerometer is outputting, but the sum is only 0.17. Multiply that by 11, you get this. So that's the output of the op-amp. And then when the accelerometer is 1.47, the op-amp will be outputting 3.74 volts. Okay, just hold on, it'll make sense soon enough. Okay, the last part of my circuit is the voltage regulator, which is the NTE956, which is an adjustable 3-terminal voltage regulator. Its output range is, it can go anywhere from 1.2 volts to 37 volts. And it has a max output current of 15 amps. Minimum load, I'll get to that in a second. And then it has a ripple rejection ratio of 80 dB, which is pretty damn high. Well, I don't know, it just seemed high. Okay, just for you guys who don't really remember regulators, we did that like in what, week 3? This is a fixed voltage regulator. So basically what it's going to do is, it's the LT1083, I don't know. This thing's always going to output 5 volts. That's what a voltage regulator does. It'll take an input and it'll give you a steady output. So no matter what you put over here on this input, even if it was 100 volts, well theoretically, if it was perfect, then you would get 5 volts out on this fixed regulator. It's always going to give it 5 volts. Now what I'm using is the same thing that we had in our circuit, which is an adjustable voltage regulator. Right? So this is just an example of an adjustable voltage regulator. So the formula, if you guys forgot, it's Vout equals Vref times 1 plus R2 over R1. And Vref is this little voltage across R1. And normally it's 1.25 volts, but it's part specific. Anyway, so on this thing, on this circuit, right, if Vref is 1.25, I have an R2 of 3K and an R1 of 1K, then this just turns to 4 times 1.25 is 5 volts. So this is kind of like the circuit you'd have to do to get a 5-volt steady output using an adjustable regulator. And once again, the input wouldn't matter, it's just going to give you 5 volts. And that 7-volt drop is dissipated by the voltage regulator in heat, or I'm pretty sure heat. Okay, so this is my actual circuit. And what I'm using is I have an R2 of 100 and R1 of 1.5K. So if you do the math, this right here, from the top of the output to the ground, that is a potential difference of 1.33 volts. Okay, so now to tie them all in together. So how's this circuit going to actually work? So the thing with this circuit is, using the regulator, I can have a constant voltage and it will hold it there. It won't fluctuate because the regulator will handle that. And it can deliver that variable amount of current that I'm going to need, that I showed you guys, that it's going to go from 0.4 all the way to 1 amp. And I can't do that with an op amp. I mean, it'll blow that thing up. It can only deliver like 25 milliamps. So, this is kind of like the complete circuit, and I kind of simplified it. Right? I'm not going to use the accelerometer anymore. I'm just going to call it V-sum, which is basically what this thing's going to feel. And then that, I kind of tied it to the ground of the voltage regulator. So when V-sum is 0 volts, right? This thing has a gain of 11, so it's right here. It's going to be 0 volts as well, right? And then the difference between this point to that point is 1.33 volts. So the motor, when this is 0, will feel 1.3 volts. Okay. Next one. So when V-sum is 0.17, which is when it's flat, it'll go into the op amp. The op amp will multiply it by 11. Then you get 1.87 volts at the bottom. Just adding 1.33, then the motor up top right here will feel 3.2 volts, right? And then the last case is when it's going up, and V-sum is 0.34. Multiply that and then add that, you get 5.07 volts. So that's essentially how I'm going to make this thing work. Just based on the tilt, this whole thing is basically a huge amplifier, right? So when it's going up, it'll feel 5 volts. When it's flat, it feels, when I say 3 volts. And when it's going down, it'll feel basically 1 volt, right? So that power difference is what's going to drive the motor train faster or slower. So this is my actual circuit. I didn't want to explain this. It's not really that pretty. I have capacitors in here to deal with like tactless filters and a bunch of other stuff. But it's basically like the previous slide. This is my simulated data. The bottom one is I think that's V-sum. This one's the op amp, and then this is like V-out, the entire V-out. So my circuit actually isn't 1 to 5, it's 1.42 to 4.6 volts. That's what it's going to be outputting, and the range will be 0.2 amps to 1.1 amp. Oh yeah, the minimum load current. Okay, the thing with the regulator is, if V-out is an open circuit, it tends to fluctuate, so it needs to kind of have a minimum load current. So you have to stick a resistor at the end of it, so that that voltage that the regulator is outputting, it goes and dissipates somewhere else. But it's not really important for this. Bill of materials, there's my regulator, accelerator, op amp. You're going to need a motor, probably a gear train. Caps, a potentiometer, a few resistors, and that's basically my entire circuit. It's very simple in the fact that it doesn't use like transistors or anything, quadratic or differential. Lastly, I wanted to thank Dr. Finkenthal, who's not here, but he was kind enough to let us use his lab to construct the accelerometer circuit, and he also helped me out with the motor problem I was having. I wanted to thank David for being nice enough to give me a rail-to-rail op amp because I was not using that. My parents, because they definitely financed a good portion of this entire thing, which was kind of cost-heavy. And then, of course, Professor Alex, because he's put in almost as much time into this thing as I have in the electrical circuit portion. Yeah, and that's it. So if I can get someone up here to help me put the ramp up, then I can show you how this thing
He didn't think you. You didn't think your girlfriend.
I know.
SMH.
Thank you.
It's whatever. You better hurry up.
Yeah, better hurry. I'm gonna put Bill in this
You guys
video.
have, like, 2 minutes set up.
Say hello.
Oh, last
Say
episode,
hello.
do you guys have any questions?
Say hello.
No, it's good.
It's gonna be on YouTube.
Yeah.
What do you mean by parts? Like electronically? Man, the car, it's hard to say. The tires themselves, I got them from a hobby shop and they cost me like 35 bucks just for the 4 tires. Everything else I kind of like got together. Yeah. Now I know what you guys think of me.
How come it's in
Because I think
Why doesn't it roll down?
Huh?
Why doesn't it roll
Oh,
down?
it doesn't roll down because
The axles are tied to the motor.
no, well, yeah, they're all tied to the gear, and the gear from the tire to the motor has a gear ratio of 108. And these rubber
Okay.
bands, they were my godfather's idea because then it's kind of like 4-wheel drive. It takes more energy to kind of roll it down.
Cool.
Yeah, I guess I might as well just show you guys the battery. What it does normally.
I don't think you're gonna fit it on there.
Okay, so this is what I was talking about when you just have 2 batteries connected to the side. So right here it's drawing almost 4 watts of power. At the top it's 1 watt, half a watt, and that's it. So,
I can't see.
yeah, it's a totally legitimate question. No, actually the flux capacitor in there, it doesn't allow it to do that. Exactly. Then it somehow gets 88 miles per hour. So. Okay. Sorry, I just have to. I was originally going to have this thing battery powered, but the thing is, this thing sucks up so much power. I mean, the batteries will almost be dead by the time it's over. And I mean, somehow I was using another power supply, and somehow I blew that thing up using this. I really don't know how. It just, one day it just stopped working. I was like, okay, guess it doesn't work anymore. Okay. So, using my circuit now, you should see kind of an eyeballed constant speed. So, what the heck? Oh.
That's constant.
Should probably turn these on. I hope this works. Nope, not working.
Wait, do you need to plug it in?
Hmm?
Do you need to plug it in?
It is plugged in, right?
Resistor.
It's on?
Yeah.
Actually, I also wanted to see who was paying attention. So, I'm going to go down to my circuit.
Stop.
Yeah. I didn't get it going down though.
So,
I just got it going
man,
up.
I guess you can't see.
Yeah, I couldn't get it over there.
Okay, so, my amplifier circuit R4 is 10K right there. So, if I change that to 5K, what would happen? Anyone want to take a guess?
I thought I was going to raise it because it was divided by each.
We're gonna change the gain factor.
I'm going to change the gain factor.
You want it to be 11, right? So.
Yeah, so if I change it to 5, I'm pretty sure it'll be 6. So, okay. So let's just see what happens when I change the resistor. You're doing what to the circuit? If I change the resistor, R4, which is basically the feedback loop into the op amp, I half the gain of the op amp. So this is what half the gain of the op amp will do. So, yeah, and so instead of a 5K, if I put a 20K
Oh, snap.
right here, now I have a gain of like,
Dude, watch out, Anthony. Not fly at you.
I'm gonna have a
Getting really terrible.
I'll have a gain of 21. So this is what it kind of does on steroids. That would have happened. Okay, so it's in the right term. Okay, so last question. Does anyone else know how motors work? And by that I mean if I switch the polarity on the motor, if I just I kind of invert it just by switching, you know, the poles, what's going to happen?
It goes backwards.
It's a question.
It's actually gonna fly off the table.
The other way. The motor will turn the other way.
Yeah, it's going to fall.
It'll
So,
actually-
what will the car do?
But didn't you set it so that it senses the difference? So won't it speed up?
Yeah, but if like just the terminals, just the final thing right here, if I switch the terminals, like David said, it will spin the other way. So, okay, that was, yeah, it's not gonna work. Alright, well basically it was going to spin backwards, but right here would have stopped. And does anyone know why it would have stopped right here?
Because the accelerometer is only set for one.
Yeah, it's still referencing it.
Yeah, so it doesn't care which way it's going. As long as it's facing this way, to the accelerometer, it's on descent, so it's going to lower the voltage and it won't give this thing power to go back up. And that's my project. Mitch, be on me.
Can I stop it?
Nothing.
Do I stop the recording?
Yeah.
Uh-oh.